Okay. Guess there's a lot of people at the career fair today, and I'm happy that the setup here I can kind of encourage that a bit. Like I said, like I've got an echo. How about that? Maybe no more echo. Like I said over the email yesterday, rather than giving like a in-class handout, since a lot of the class was planning to attend the career fair, I'm going to post a Moodle quiz of some sort based on a problem we'll talk about today. I'll post that this afternoon, so you'll have today and tomorrow to fill that out and put your answers in. I'll give you a few minutes in class today to kind of start working on that problem. I'll take you through some of the steps, and then it'll be up to you to kind of finish it out and carry it to an answer. I'm going to revise the numbers just a bit. We'll work through that. But I was also taking a look at our syllabus, and I've posted a revised one because we've actually made better time than I intended, I guess. So we've already covered pretty much sedimentation and coagulation by now, and we're even just starting to talk about flocculation last time. So today we'll touch just briefly the coagulation side of things and really cover most all of flocculation, have those problems, and next time we meet, I plan to finish talking about flocculation, kind of work through those problems, make sure that's clear, kind of go through that participation assignment, and then basically we've covered the material that I planned for exam 1. So I'm going to move the exam review to be in person here instead of the virtual idea that I had. We'll probably next time also begin talking about granular filtration, which will be on the second exam. But just as kind of a topical, okay, here's what's coming next, and try not to distract you too much with the math on that front. So that's kind of my plan and our outlook for the next couple lectures. Any questions or concerns on that? Yeah.
What's like the format of your exams? Is it like written out?
Yeah, so the exam format will be fairly similar to some of those word problems on your homework, where you'll have some problem and find this part of the answer, and then kind of continue, find the next part. I try not to make it so that it's answer B is dependent on answer A. Sometimes that happens, but what I'll do when I'm grading is to try to account for, well, if you did get A wrong, but you had the process right for B, you usually get most, if not all, the credit. So I'll be looking to assemble it, hopefully without any of that interdependence, but sometimes it'll happen a little bit, and I'll account for that. So it will be primarily word problems, calculations. I keep most of the more topical, subjective manner that it's more like flavor added. We'll talk about the Flint water crisis, for example, as participation, right? And so really what I'm testing you on is your ability to take these mass balance tools and the different tools that we learn along the way and apply it to some problem. So that's the objective I have for the exams. And I usually aim to make them manageable in a class period. If you happen to be really struggling or didn't study at all, you might feel like you're out of time. If you feel really good about it, confident about everything, hopefully you'll have plenty of time to spare. That's kind of my target. Sometimes I miss the target, and I'll adapt with you accordingly, or it'll just be easy, right? So sometimes that happens, but my target is to be a challenge, but I give a lot of partial credit as I grade. So it's a challenge that I'm using to see how much you learned. So we can talk certainly more about that. If you've got any other questions right now, happy to answer them, but we will cover more of that during the exam review as well. All right, so last time we got to talking about flocculation. We covered the sedimentation and kind of those reactors, coagulation being ways of causing particles to stick together. So today we're going to look into the math of, okay, when they're starting to stick together, how do we quantify that? How do we predict that? And have some meaningful result to say, well, we started with these really small particles, then we sent it through this process. What size are our particles now, and are they going to be removed from our sedimentation? That's sort of the goal and the process here. Oh, and one other thing, so as you know, the homework's due today, so I will be also posting a second homework assignment that will be due on our exam review date. So back to this real briefly. So we'll have, I'll post a homework today, and you'll have a full week to turn that in by the 21st. Okay, and that'll cover the sedimentation, coagulation, and flocculation, whatever we didn't cover in the homework one. Okay, so now that we're aiming to cause the particles to stick together, we talked briefly, we talked through this slide already. We want gentle mixing. We're going to reduce the number over time. That's going to increase our size because it's 2 particles become 1. That's a bigger particle. That's fewer particles if we're counting them by the number. All right, so then we're really looking at the K, because in any sort of a system we might have, if we have some sort of a reaction rate constant there, we are assuming that K will depend on how many there are in the system. So it's going to be a first order rate constant, or first order rate. And it's also going to be reducing the number because they're sticking together, right? So that means it's a first order decay. So that's kind of our assumptions there. We looked at the mixing intensity, the mixing conditions. We said we have this parameter G as the mixing intensity, and that's going to be a formula on your exam sheet. And you'll need to know, okay, when and how do I use this? What units am I putting in? What is this P? That's power in watts. So we'll take a look at this in a moment in our example problem. Okay, so then we got to this point to say, well, we're going to start with some number of particles in a given volume and end with some new number. And I drew up the example. We had a few particles. We'll say, I'll put 8 here. And now we have 2 particles each that comprise 4 new particles, right? So an initial was 8 particles per some volume, and final in this case would be 2 per some volume. So we can look at that and say, well, there's 4 particles in each of the new aggregates, if these guys are aggregated particles. And these ones are the initial particles. Then we know something about how many of one are in the other. And this gives us a way to compare the sizes. So if we knew something about the initial size, then we stick them together. If we know how many go from one into the other, then we have a handle on the size of the new ones, right? So this is all about controlling and managing the size of the particles we result with. So these collision reactions will give us that info to understand the size of the new particles. Now, of course, you could do a reverse engineering sort of situation and say, well, I know my system can settle this size of a particle, so how long do I need to let them flocculate, or what conditions of flocculation will be sufficient to get it there, right? So whenever we're dealing with one of these problems, we're not necessarily looking at the same exact endpoint each time, right? Our design task might be, well, we know we can do this, so how do we get there? Or maybe I say, given this flocculation situation, what's our resulting particle size, and will that settle, right? There's a lot of different questions, but all oriented around the same sort of mass balance here that we can use with the flocculation to know something about these final particles. So that's where our mass balance is going to come into. And we can do this, of course, we can put it into a batch reactor or a CSTR Most commonly in practice, we'll use a CSTR. But maybe you decide, point of use treatment, we might do it in just one jar or one bucket. So there's certainly, as with any of these reactions, the reaction itself can be put into different containers, different reactors. So we said that in this scenario, if we look at n naught over n, in this case that's 8 over 2 or equals 4. So each of the new particles has 4 of the originals. And we can, so we did that last time. And I'll say that given that it can be in batch or CSTR or plug flow, whatever, let's take a quick look at what that would look like, right? So in a batch scenario, we're going to have some accumulation term for the number of particles in that volume over time. And we would describe this as a decay reaction in that volume that has that rate constant times the number of particles in there. And it's a decay reaction, so it's negative. And the n is raised to the 1 power here because it's a first order. It's first order because it depends on how many particles are there. And we will also see that our reaction rate constant has units of per time. I think we got that far. Maybe we didn't quite get that far last time, but we'll see that in a moment. So these are first order decay reactions. Should make sense when you think about particles have to be able to meet each other, so it does matter how many particles are in there. Okay, so in a batch system, this is all it is. We would cancel the V's, then we would do our typical integration, dn over n from n naught to n equals minus k dt, and integrating that from 0 to time t. That gives us our very typical n equals n naught times e to the minus k t. So you've seen this before, and of course, if we wanted to do this in a plug flow reactor, it's kind of weird because we want it to be mixing. So this particular scenario is weird to think about in a plug flow. It's probably not as relevant because we want the whole solution to be mixed. But normally we could insert theta for that for a plug flow. But from this point, we actually, instead of relating it to n over n naught, we would want to relate it to n naught over n, because that's, like we said last time, that's the meaningful language, right? That's how many of the initial ones are in each final one. That gives us that size comparison nicely. So in this case, we would actually divide both sides by n and get the n naught over n term by itself, and that would be 1 over e to the minus kt. And you could probably invert that just by getting rid of the negative. So that would be the scenario if we had a batch system. And in a CSTR system, we will see an example of this. This will be the more common one. And as I said from when we were first covering mass balances, the first order decay at steady state in a CSTR is a very common equation we'll see repeatedly in the class, and here's one example of it. So we would, in this case, the batch I should have drawn in the first place, is just a batch of water. It's got some volume, and it's got some reaction rate constant. In the case of a CSTR, we have flow through, some volume, it's mixing, so we have a flow, we have an initial and a final, and some reaction rate constant in there. So given all that, our CSTR equation we would first, in general, assume we can manage a system where it's at steady state. The amount of particles coming in is relatively constant. So the number there, we're causing this reaction to change it, but we've reached kind of that equilibrium point where the amount of change is kind of constant by this point. So we're not accumulating any stuff, so we'll say steady state. That means our v dn dt term goes to 0, so no net accumulation. There's particles there, but we're not getting more and more and more particles in there over time. So then at steady state, that's equal to 0 is equal to the inputs, Q n initial minus Q n final. And then we're going to add whatever reaction term, and this is a decay term. So we're going to say minus in that volume times the K times the n to the 1 power. Right? That's the term that we add in either case. In that volume, we've got that reaction. So that's just the reaction term in the context of a CSTR. That's just one of several components adding or subtracting to what's in there. So in this case, if we want to solve for n naught over n, I like to clean it up first and say, let's divide everything by q. So we'll say 0 equals n naught minus n minus v over q becomes theta, right? V over q is theta. So this will become theta kn. And I'm going to get n naught by itself. You can subtract it from both sides, and then you'll notice you've got negatives everywhere. And so you could divide everything by -1, or you could, or multiply, or you could simply add these two to the other side and then just swap sides for convenience and say n naught equals n plus theta kn. And you notice there's an n on both of those terms. That makes it very nice and easy just to divide everything by n, and you get your desired n naught over n. So we will take from here and say n naught over n is equal to 1 plus theta k. This should look very familiar to the 1 over 1 plus theta k that we did last time when we had the inverse of this and when we solved for n over n naught equals 1 over 1 plus theta k. Now that's the form we'll usually see it in. So normally we're interested in seeing what amount remains, like how many particles are remaining, right? Or how many bacteria are remaining. In this case, we don't care as much about the number remaining or the fraction remaining. We're reducing the number so that we know something about how big the final product is going to be, the aggregates. So we're just going to arrange it based on what we need, right? So we could look at it in either sense. That's just the derivation for what we're going to need in a flocculation for the batch case or the CSTR case, right? Does that make sense? Blank stares. I'll say at least no questions, right? Okay. All right. So moving on from there, the question remains, okay, what about this rate constant, that K? What's up with that? How are we going to determine that? And this is where we have to get into a bit of math to find that K. And this is just going to be based on some of these parameters we've talked about, this mixing intensity. The reaction is going to move forward in some way that depends on that mixing intensity, right? We talked about that. And so the way we're going to account for that is to put that mixing intensity into this rate constant. So for a given condition, we have a given rate constant. The other thing that it's going to depend on, there's two other things. One is how much of the volume of water is actually occupied by these particles, right? If it's 1% of my total water, there's a lot of particles in there, and there's a good chance they're going to be meeting each other pretty quickly, right? If it's, 1/trillionth of the volume in here is occupied by particles, that's not very likely that they're meeting each other. So that there will be a dependence there. And it's kind of like a percentage, what percent of the system is particles. And the last one is how likely are they to actually stick together when they do encounter each other? And that goes back to our coagulation. When we were talking about stabilized particles versus destabilizing particles, this term here is going to be our collision efficiency. That's telling us how much did our coagulation work to destabilize the particles. And we define that from 0 to 1. So it's just a fraction. 1 meaning 100% of collisions result in a new stuck particle, a new aggregate, right? So when one particle meets the other, they're Velcro and they stick, right? They're matching Velcro. Whereas if we did a decent job, halfway decent, the particles, half the time they stick, half the time they don't and bounce off, then that would be 50%. So it'd be 0.5. So this is just a term to tell us how many times do the particles stick together when they meet each other. Is it 10 out of 10? Is it 1 out of 10? Is it 8 out of 10? So this is just a fractional form to describe that. 1 is 100% of the time they stick together. That's complete destabilization. And if they're never sticking together, this becomes 0. And then our rate constant becomes 0, which should tell you if they don't stick together, we have no rate, right? We're never going to have this rate in action because it's not possible. They don't stick together, right? So that's kind of the tangible look at our coagulation effectiveness. Okay, so that's just going to be a value from 0 to 1. That's all it is. Doesn't have any units. It's a fraction. It's never going to be above 1 because you can't have two particles meeting and suddenly that means there's like two, that just can't be more than 100% of the time, right? That they meet and make a new one. Next would be the flock volume. That's what I mentioned about what portion of my volume is actually occupied by particles. And so this one is a strange one. It's called a volume term, but it's actually going to be unitless. And the way to understand that is, as I was saying, what portion of this volume is occupied by particles. We can describe the volume of the particles and then divide that by the total volume of my container, and that's going to be a fraction, a volume fraction. And so this is essentially, even though it says flock volume, we would say this is a volumetric fraction, or the volume fraction. So in order to have this truly actually be unitless, here's one thing to pay attention to. We have to make sure the volume terms are in the same units. So if we have some number of particles per milliliter, but we have a volume in cubic meters, we better convert from the milliliters up to cubic meters, right? So there's going to be some unit conversion here, very likely. So what we define this as then is basically the volume of one particle times how many particles there are given a certain volume. So if I had 10 particles in here, each 1 milliliter, then I've got 10 milliliters of volume of particles in 1 liter total, right? So that would be the direct interpretation here, and we see that from this equation where we have pi times the diameter of the particle cubed divided by 6. That is the volume of one of these particles, right? That's a sphere. We're going to assume always that we have spherical particles. Even when we create a new clump, a new aggregate, we always assume that somehow we made a new sphere. That's going to keep our math very simple and in a way where we can manage it. So I'm just going to write this up here. Assume spherical particles and aggregates. We also assume that when we do stick particles together to make this new spherical aggregate, that the volume is conserved, right? We're not losing any volume, even if maybe it's changing shape so that we can imagine it's a new sphere. So we'll say, and the volume of particles is conserved. Okay, with those two assumptions, that gives us a way to relate the initial diameter to some final diameter. And as you recall, this diameter is what's pretty important for sedimentation. That was one of the predicting values of how quickly it will sediment. So we're trying to increase that. All right, so the flock volume, back to this. We have the volume of one particle times the number of those particles in the volume. So we'll say volume of one particle times the number of particles per volume. So when I say volume of one, we could say volume per one particle, and that will make the units make a little more sense, right? So I'm going to rewrite that and say volume occupied per one particle. So if we multiply the volume per particle times particles per volume, we see that we become unitless, assuming we have the same units across. So I'm going to go ahead and say, let's get this into cubic meters and cubic meters. Chances are that's going to be what we need to work with. So there will be some unit conversions there for sure, but once you do, this becomes a pretty straightforward, simple equation, and that's the basis of it. All right, does that make sense? So we looked at last time how to calculate the G. That's the mixing intensity. We have that formula for that. That G is in per time units per second. We saw that that's kind of that gradient, that velocity gradient. You know, we looked at that last time. So our K, if we take a look at the units, this guy has no units. It's a fraction. What fraction of the time do the particles stick together? 4 is just a number. Pi is just a number. Omega is also just a fraction. What fraction of volume? Volume fraction. And so G is the only thing that gives our K here a unit, and that unit is per second. So overall, our reaction rate constant is in per second units. And that kind of tells us this is a first order reaction, if we did not already know. Okay. Good with that? So a lot of unit conversion stuff, but otherwise it's a little bit plug and chug here. And the real challenge with any of these problems is understanding what the language of a word problem is talking about, translating that into the math that you need to do. Okay, so let's practice that. What I'm going to do is I'm going to take this problem. I'm going to revise it just a bit for you to work on it. What I'm going to do is give you a new diameter here. And say, let's start with 0.015 millimeter silt particles. These are very similar to the ones we did, you know, in the sedimentation problem the other day. And we're going to take a look at this problem, and I'm going to give you essentially this problem as your Moodle assignment. And I'll post that this afternoon. You'll have tonight and tomorrow to do that. I'm going to ask you a few parts of that question to ask you, let's say, the mixing intensity, this part, that part, and the other part. I'm going to walk you through part of it today, but not actually solve it. So you can check, you can spend 10, 15 minutes working on it now. I'll walk you through a few steps and you can check how closely your work is aligning with kind of the right trajectory, and then you can wrap up on your own time and give those answers. It'll be some sort of a timed quiz. You'll have these slides to kind of look at what's happening here, so you don't feel like you have to sit there and answer everything in the 5 minutes or whatever the time quiz. Be prepared beforehand, and I'll write up what specifically I'm going to ask right here. Okay, but let's take a look at the problem itself, and I'll give you a little bit of time to work on it. Okay, to improve the settling of these particles, we are going to completely destabilize them by adding alum. So note that's a key word there. We just talked about it. That's telling us the collision efficiency. And it is passed through one of two side-by-side, well-mixed flocculation chambers. So That tells me I need to draw this out so I can visually see it and track what's happening here. The chambers are cubic, each with a dimension being 3.5 meters. They are mixed with paddle mixers that input 2.5 kilowatts of power into the water in each chamber. The water entering the flocculation chamber contains 10 to the 5th particles per milliliter, and the question is, what is the average diameter of the aggregates leaving the chambers? So it sounds like a pretty simple question, right? Okay, what's the size? As you'll see, there's actually a lot of steps to get there. I'm gonna just give that to you here. I will jump in a few minutes and write a few things up to take a look at and discuss a little bit of it with you. You are welcome to ask some questions and even brainstorm together right now if you'd like. So like I said, this is a time where you can kind of test yourself on how well are you putting these pieces together. And then I'll give you some guidance, and then you can, with the Moodle assignment, you'll be able to kind of see how well you're able to finish that out. I'll write up a few of these equations that we've discussed up here. And I'll plan to give you about 15 minutes to work on this. All right, so how do you feel about the problem? Do you feel like you got towards an answer or halfway there? What do you think? Maybe? Some good, some not so good?
Almost there. Okay, is the n initial? Can you explain that?
Yeah, so the n initial is basically the number of particles per volume coming into the reactor, right? So if we draw this system, which is probably the first thing you should do, it says we have two side-by-side identical flocculation chambers that are cubic. They are well mixed. They have some volume that we can find. That reaction happening, K, and water coming back out, right? So we have two of these. And presumably these will probably join and continue. Now, in each of these, we have some initial number concentration of our particles. This would be the Q total, and then it's split into half, so 1/2 Q into each of these. And we also have some initial number of particles going in. So that would be N naught here. Splitting the concentration, splitting the water into two parts doesn't change the concentration, just the flow rate. So we're still going to have N naught in either case. So really, I'm getting further than your question here, but we should look at just one of these systems. Since they're identical, we just need to look at one of them given its particular flow, and then we know what happens with the other. So then we have some N coming out, some N coming out, and it's going to be N coming out, right? Maybe 1/2 the total, Q. Does that help answer your question, or is there something else you want to know about N naught?
Well, for this problem, we're going to put the whole flow through one of the reactors.
This one said that the particles in example 1, which was 3 cubic meters or 3 million gallons per day, is passed through one of two side-by-side well-mixed chambers. So it's a little vague. I'm going to ask you to treat it as if we're splitting the flow in half there.
Then next question is, so this is N naught here the same as like the I don't know, I forget what that's called, it's a little omega sign.
Yeah.
Flock volume. Okay, is that the same as whenever you find the expression, rate expression?
Yeah. So this N naught, we're dealing with the same N naught here.
Okay. Make sure that they're the same.
Yeah, and we see it's actually given to us right here. So we can look and find N naught should be 10 to the 5th particles per milliliter. So some number per milliliter, right? Yeah.
So if you treated it as like one big system, would you just cut the thing in half at the end?
If you treated the problem as like one bigger chamber, the problem with that is the different inputs into a given chamber, the power, for example, if you look into our mixing intensity equation, we have it drawn up there, that depends on the volume of that chamber.
Gotcha.
And so you actually can't, if nothing like that was a factor, then maybe you could double the volume and it would just be kind of the same thing, right? But since there's some dependence there, we do need to account for it. So good questions. Okay, given this drawing, how are you feeling? What else are you getting stuck on or have questions about?
The only unknown is the final volume. I can't find any equation to relate it because I already used the rate expression.
The final volume?
The final particle number.
Okay, N. So you're looking for N and trying to figure out how to get to that, right?
Yeah, I just built in an expression to label.
Okay. Yeah, that's a very common thing to look for and try to, and end up getting kind of stuck looking for here. And actually what I'll say to you is that you don't ever, in the flocculation problems, maybe you could take a route where you solve for n, but really what you need to do is find a mass balance that will give you the ratio of n naught to n. So you don't actually have to find just n by itself, ever. And that's one, it's a great question, because that's the next step I was going to take you to is, well, we can find the g and the omega and then therefore get the k, but what are we putting that k into and how are we using that to aim towards our problem? And that's going to be a mass balance on one of these chambers. So we'll say on one chamber to find the value of n naught over n. And what you'll see there is what you might be tempted to do is to say, oh, well, I have n naught, so if I find n, then I have that value. But you don't actually have to go that far if you set up the mass balance, like we were looking at a moment ago up here, further, where we derived a mass balance for one of these systems, right? So we can go through that same process. Oops, sorry, hit the wrong button. We can go through that same process and say 0 is Q. I'm just going to write it as Q. This is Q into one of these chambers. Qn naught minus Qn minus Vkn. Like we saw, we can derive that to some expression of n over n naught. Excuse me, n naught over n in this case. And we said that was equal to 1 plus theta k. So we need to solve for theta, and we've done all this work presumably to solve for k, and then we can put it there. So once we have that ratio, then we know something about how the volumes compare. So we'll need just a little bit of geometry about spheres, and we'll be good to go. So in essence, we can say the volume of any aggregate is going to be equal to the volume of the individual particle multiplied by the number of particles per number of aggregates. And that makes sense on a physical sense, right? We said volume's going to be conserved, and we're going to treat them like spheres. You know, the new aggregates will just meld into a new sphere somehow. And so this is just very simple, right? The volume in an aggregate equals how many of the initial particles are in there times that volume. But what that does for us is gives us a way to compare the diameters, because the volume of a sphere is pi times the diameter of that sphere cubed divided by 6, right? So then we can solve this equation for the diameters involved that we're looking for, and noticing that this number of particles per number of aggregates is essentially n naught over n, which is why we wanted to solve for it. So it might be, one thing you could do is try to look at the very, very end of the problem to say, how can I get that solution to the diameter? Okay, well, there's spheres. I can relate those if I know how many of the initial are in the final, and just backtrack from there, right? Whichever way it makes sense in your mind, like sometimes you have to kind of reverse engineer it. Does that kind of make sense of the process there? Yeah.
Is that like a typical range that K is usually for a certain type of reaction?
That's a great question. So K for a certain type of reactions, the range, it really kind of depends. In this case, K is in per time units. Trying to remember. A lot of times it's going to be some fraction, like less than 1, maybe less than 0.1. In this case, I think it is below 0.1, so 0.01 something, or something like that. So if you're getting K of 1,000, go ahead and check your unit conversions and things. If you're getting it 10 to the minus 10. Check your unit conversions. There are chemical reactions that have that are very rapid, that you'd have some like very large or very small number accordingly. So it can be pretty wild, but I think in this case it's something like 0.01 or something like that. Okay, so then what you can expect on the quiz assignment thing will be something like a lot of these parameters that you had to solve for. What I'll just ask you to do is make sure you, for your own sake, highlight what step along the process, what were the values for each of these, right? So things like K, omega, G, and not over N. I might not ask every single one of these, but ultimately I'll be checking kind of steps along the way. And then of course the diameter of the aggregate itself. All right, so yeah.
Is the volume of the particle the original, like the 0.015 that would use that diameter?
So the volume of the particle itself, like the initial particle, what we're calling particles is the initial stuff. Yeah, so this 0.015 millimeters, that's going to go into the volume of the particle. Yeah. We could write that as pi times dp cubed over 6, where this guy is dp. All right. How do you feel about that? Is this feeling useful? Good. All right, so there's just really one other side topic here I wanted to talk about, given that we kind of introduced like, oh, what happens if we branch this flow into 2 different chambers? Haven't really talked about that. Kind of makes sense once you draw it out. That kind of thing might happen a lot when we encounter a problem, particular scenario. And I wanted to highlight, well, what happens if we have sequential reactors? Because there's something kind of neat that we can do with sequential reactors. If we know something about them, we can combine our solutions into one simpler solution in many cases. So let's imagine we have a couple flocculation basins where we want to know, or maybe this is, we'll use some other, it could be flocculation, could be something else. If it's flocculation, we usually care about N naught over N, but most of our systems we're going to care about maybe like disinfection. How many are we left with at the end versus how much we started with, right? So in this case, we'll say we've got N0 here, or N naught, N1, N2, and we could add more, but we just have one flow rate going through the system. We have some volume 1, volume 2. We might have one particular reaction in here, a different one in here. We could look at a system that might have different dimensions and all that. And that would correspond with some theta 1, theta 2. And if we look at this particular case, this is showing 2 CSTRs in series. We know that we can often find something that looks like N1 over N naught. We've talked about that a lot by now, right? And so if we assume, for the sake of this exercise, that we have first order decay reactions in steady state systems, then this becomes very much like what we've seen before, right? We've even just talked about this today to say, well, that N over N naught, we can derive that and get 1 over 1 plus theta K. This time I'll label it theta 1 K1. right? That corresponds to the solution, the mass balance solution, if we're interested in what's coming out of the first reactor compared to what's going into it. We can do the same thing with the second one to say N2 over N1 is 1 over 1 plus theta 2 K2, right? Pretty straightforward. We kind of knew that. So what about solving for N2 over N initial? Well, here we might recognize that there's a nice little multiplication we can do to get there if we know something about N1 over N naught and N2 over N1, right? And you can probably see that immediately. We can cancel some stuff. We can cancel the N1s. That becomes N2 over N naught, right? Now, to put this, to put it into practice and say, well, yeah, that thing equals itself. Great. What use is that? We can say that we can substitute in these terms, right? We can say, well, the N1 over N naught was 1 over 1 plus theta 1 K1. And we can multiply that by the 1 over 1 plus theta 2 K2. So we have a pretty simple way to say, okay, let's just multiply. Now that we have them as ratios, then we multiply the actual nuts and bolts of the system, the 1 over 1 plus theta K, for each reactor. And if we have a system where they are identical, so we just make them the same size, we give them the same amount of stirring, the same reactions happening in each of them, or something like that, we can simplify this much further and say this is 1 over 1 plus theta K, because now the theta and the K will be generalized. That's theta 1 equals theta 2 and K1. That might not always be the case, but if that happens, then this is just 1 over 1 plus theta K squared. So it becomes pretty convenient, pretty simple to combine them that way. We could have a system, and we'll look at one briefly in a moment, where you could have a CSTR and a plug flow reactor next to each other. And you just take the same approach. You say, well, I know the ratio on this one and the ratio on this one, so let's multiply this by the next one and find our answer that way. Okay, make sense? You could have a lot of these. In fact, if you made an infinite number of CSTRs in series, I guess they're just really tiny, like infinitely small, and you made an infinite number of them, you'd put an infinity here, and that's probably, I don't recall the exact mathematical route, maybe that's a Taylor expansion, whatever it is, that would get us some recognizable form. So if we were to take this and say, if an infinite number of identical reactors, that actually gets us to the scenario where we have a plug flow reactor. It just acts the same way. It's a different mathematical way to get to it, but it will yield us the same exact equation that looks like a batch reactor just floating along across a conveyor belt through the system. So doesn't, I don't really need you to know that derivation or anything, but it's kind of a neat look at how the math will work and why we can derive a plug flow reactor in a couple different ways to say it can be at steady state with flow through. You just have to have an infinite number of these little, this one's mixed, got flow going through it into the next chamber, it's mixed. That's pretty much the same exact situation as a plug flow reactor. Okay, so let's take a minute and I'm just going to work this one with you to approach it, just to kind of get a feel for what this would look like. So if we consider a sequence of two 8 cubic meter reactors, each with bacterial growth reactions occurring, within them with a rate constant of 0.001 per minute. If the flow rate through the reactors is half a cubic meter per second, the incoming bacteria concentration is 10,000 cubic CFU per liter. That stands for colony forming units. We'll talk more about that later. Just some unit number concentration. What is the final concentration of bacteria if the first reactor is a CSTR and the second is a plug flow reactor? And the question continues to say, will the final concentration be different if the order is reversed? Okay, so let's first of all draw that up. So we have first reactor is a CSTR. It's got some volume, it's 8 cubic meters. We have a flow rate, an incoming concentration. We have this is going to be well mixed. We have a K in here, and so we have some N1 leaving it. Then we're going to go into a plug flow reactor, and we could draw it in a variety of ways. I'll just draw it kind of as a long, thin pipe and say that's a plug flow reactor. The volume also is 8 cubic meters, and we have some N2 leaving it. Also have the K, it's the same K. We also have the flow rate. And so in both cases, we have theta is V over Q. And so, you know, the theta for each of these, we could have a total theta across the entire system, but I'm going to call this theta as the theta in one particular chamber. It's going to be the same regardless. That's going to be the volume, 8 cubic meters divided by the 0.5 cubic meters per second. So that'll be 16 seconds for each. Okay, so that's just kind of sketching it out a little bit up front. And then I have to start thinking about, okay, well, what's the scenario here? And we want to know what the final concentration of bacteria is at the end of the entire system. So we want to know what N2 is. And we can approach that in a similar manner as last time. As we were just talking about, and we should be able to, you know, we could do one of two things. One, we could try to combine them up front, and it should work, assuming we've done everything algebraically correctly. We could also just go ahead and solve one, and then solve the next, and just take our time with it, right? So either way should get us to the same solution. We know that we can do the thing we were just talking about, and 2 over n naught should be the same thing as n1 over n naught times n2 over n1. And so we can derive equations for each, right? And this is a growth reaction. We haven't done much of those yet. So we could say mass balance on CSTR. We're going to assume this has reached steady state. So this is going to be Q going in minus Q going out, plus our reaction term, which this time is a positive. So that's a VKN. We were given a reaction rate constant in per minutes. So we know this is a first order, so that we know that that's n to the 1 power. Put in that reaction rate. So we can then solve this for, and that we could call this N1, by the way, instead of just the generic N. So we can divide everything by Q. Say this is going to be N naught minus N1 plus theta K N1. We want this in N over N naught terms. So we're going to factor out, we're going to separate and then factor out. So I'm going to go ahead and just add N1 and subtract theta K N1. So we'll say N1 minus theta K N equals N naught. Divide everything separate out that the n over here, n1 rather, times 1 minus theta k equals n naught. And so we can get our solution here to say that n1 over n naught equals 1 plus theta, 1 over 1 minus theta k. So we can put that here and say we've got part of that. And then we need to multiply it by the second part. And that part would be that plug flow reactor, which is going to be essentially our first order growth reaction in a batch, but taken through the entire theta. I'm going to give myself a little more room here and kind of revise this a little bit. So the mass balance for the plug flow reactor that's going to act like that batch scenario where we have a growth reaction, V times, VKN. This time we will say, we're going to take this from N1 to N2 as our endpoint. So when we derive this, we will see that this becomes N2 over N1 equals e to the kt. But instead of t, we're doing theta. That's because we're integrating from our starting n, which was N1, to our final, which is N2. So it works just the same. We've done it in batch systems. Just integrating on the left side, we get dn over n. That becomes the natural log of N2 minus N1. And then we can get rid of the natural log. So it's exactly the same thing as what we've seen before, except we've got a growth reaction, so we don't have that negative here. We have a positive. Okay, so with that, we can then write this portion and say this is going to be e to the k theta. Assuming we know k and we found theta, that's all we need. We can put that into a calculator and solve it. Check to make sure that our units are the same. The k was given in per minutes. We solved theta in per seconds, or in seconds. So we'd have to convert that, but that's certainly something we could do, right? Theta into minutes, and then solve. So that's basically it. Not going to bother putting in the numbers right now, but if you see this, you should be able to identify that swapping these two around shouldn't make a difference. If I've got that correct, really shouldn't matter too much which way it's going. There might be scenarios where we could have an impact, but in a system like this, I'm fairly certain you wouldn't actually see a difference. Okay, so we'll see you on Tuesday. I'm going to post that quiz.